morning. In this lecture, I am going to introduce you the linear time invariant systems and convolution operation, and I am going to discuss some properties of the linear time invariant systems. So here under the properties, I am going to discuss commutative property, distributive property, associative property, and memory property. Let us talk about the convolution operation first. Here, before starting that, I would like to review the meaning of an LTI system, which I have already discussed in my previous lectures. So this is only a brief review. So linear time invariant system. So what is the meaning of linear time invariant system? So linear system means a system which respects the superposition principle. That means if I have two signals, if I apply them individually to this system, and I will get to two individual outputs, and if I combine the two inputs and give to the system, then I will get the combined output of the combination of the both outputs. So that is called linear system. That means whether you apply the signals in isolated manner or combined with other signals, the response of the system to the given signal does not change. So that is the meaning of linear system. Then time invariant. So time invariance means if the system properties, so here the system properties are all captured in terms of impulse response or frequency response. So these two properties, they do not change with time. So for example, you have applied some signal at t equal to t1, then same signal you have applied at t equal to t2 seconds, whereas the t1 and t2 are widely separated. So in that case, so the outputs of the system, that is system response to the input at two instants, that is t1 and t2, is same because it is not changing. The system properties are not changing with the time. But in general, it is not true. In several cases, the system properties will change with time. So then those systems are called time variant systems. They may be linear. Then LTV systems, that means linear time variant systems. So what we are going to discuss now is linear time invariant systems. That means the system respects the superposition principle for the input signals and its characteristics do not change with time. Okay, under these assumptions, we are going to take up these LTI systems and we are going to study some of the properties of this. So let us consider a continuous time signal. T is the independent variable here. So T is independent variable here. X of T is dependent variable, that is the signal. It can be amplitude or voltage or current, whatever you can call. And this is here, in this case, it is taken as, it is shown as a tau. So this is also tau. Independent variable is tau here. So here I mean this can be made T also, no problem, as of T in general. So this is also, you can consider it as T, no issue. So T is independent variable, X of T is dependent variable. Now let us consider the shifting property of an impulse. So what is the shifting property of an impulse? See here, I have taken one impulse at instant t. This is at instant t. Okay, why I am able to take at instant t is here. This is, so let us take this impulse which is located at instant tau. So this is tau. At tau there is impulse, and so t is the variable. Now, so that is the reason we have written delta t minus tau. That means a delta function which is shifted in time by tau seconds. Okay, so this is what, when I multiply these two signals, that is, when I multiply these two signals, this continuous time signal and this delta function, what is happening? So this is where it multiplies at the location tau. I have an impulse, unit impulse multiplied with the signal amplitude. What is the value at this point? This value is nothing but x of tau. That means at tau, whatever x value is there, that would be the amplitude of the impulse, because initially the amplitude is only 1. So 1 into x of tau, that is the signal x value at tau, t equal to tau. So the, what is the amplitude of this impulse now? The amplitude of impulse is x of tau. Okay, so like that, if you take another impulse, let us take another impulse here, unit impulse somewhere here, again multiply with this, and you will get, let us say this is nothing but something like tau 1. Let us say this is tau 1. So this is also tau 1, and here the amplitude of this impulse after multiplication will be x of tau 1. That is nothing but signal value at that instant. Okay, so this is what is called the uh, shifting property. So basically, so shifting property, what it says is, whenever you multiply a given signal with a unit impulse, and after the multiplication its value will become equal to the signal's value. Okay, now let us take this continuous signal and represent that signal in terms of delta functions. So I have so many delta functions here. I can put any number of delta functions here, and very closely spaced delta functions I can keep it here. So how many delta functions I can keep for this infinite for this continuous time signal? I can put infinite number of impulses, any number of impulses. Very closely based means irrespective of the interval of the signal, I can put infinite number of impulses. So I can consider that a given signal x of t can be a summation or collection ordered set of all values which are equal to x of tau at instant tau, which is again multiplied by the shifted delta functions. So the tau changes correspondingly, so that it covers the total signal. Okay, so what I am doing now, what is the meaning of this equation? It is nothing but a continuous time signal can be expressed as an ordered set. That is more important, because samples you cannot put whatever way you want. They are put in the order of time. Whatever order is there here, in the same order if you put, then this continuous time signal can be represented by a set of impulses whose amplitudes are modified as per the continuous time signal amplitude at that instant. So that is what is a sum of weight shift impulses. This is the correct word to use, where the weight of the impulse is, this is the weight of the impulse. What is this one? X of tau d tau. So if I take, let us say this, if I take this, because I am taking another impulse here. So when I take this, let us say this is dt. So this is nothing but tau, and this spacing is nothing but d tau. So what is the height of this sample here? X tau. X tau is the sample, and d tau is the width of that sample. I mean, I'm representing like a box function here. Okay, I can keep one sample here. I can represent it like a box function like this. Okay, it is like a staircase waveform. So in each interval dt, I have a constant. I assume that the signal value is constant. Okay, this is because it's approximation. So here, then this is the area of each block. Then if I add all these areas, I will get the actual continuous time signal. Okay. Now let us try to find the response of a linear system. So what is the linear system? Linear system is represented by its impulse response, and you are giving an impulse to this. You are giving this box, I mean impulse of value uh, x of tau. So this is the value of the signal. This is the value of the signal at instant tau. This is the value of the signal at instant tau, and that you are applying to the system. Then what is this one? This is nothing but uh, impulse response of the system. That means the response of the system to an impulse. Now like that, you have applied first impulse here, second impulse here, third impulse here, fourth impulse here. Like that you are giving several impulses. For each impulse, for example, for first impulse, let us say the impulse response is like this. Then for the next sample, next impulse, you have, let us say its amplitude is a little bit higher. So this is the impulse response of the next sample. This impulse response of the system to the next impulse. So this is the first impulse response, second impulse response, third impulse response. Let us say this is very small like this. Okay, so like that you can build the output of this system by combining all the impulse responses. Okay, let me show it here in diagrammatically. So I have an impulse response here, h tau of t. That means impulse response of the system at a time tau, and you are giving an impulse here, or an impulse whose amplitude is x of tau, then whose output is, I mean, I can consider general variables. So here x of t, let us say I'm giving x of tau one impulse here. Okay, now the, of course, this is x of tau means one impulse at instant x of t, and I will get impulse response here. What is this impulse response? It is like a wavelet kind of thing, small wave kind of thing. This is what is the impulse response of the system. This is the output basically. Okay, so now what I am doing, I am collecting corresponding to first impulse. I have an impulse response. Corresponding to second impulse, I have another impulse response which is starting at that location of the impulse. Then I have a third impulse applied. Then corresponding to the third impulse, I have a third impulse response, a little bit larger. Then when I combine all these things, I will get the output things. Okay, so that is what is this equation basically. And what is important here, in general, the impulse response will change with the time. That means the impulse response of the system, when the first impulse is applied, there is one impulse response. At second impulse is applied, we assume that the impulse response of the system has changed. Again, when the third impulse is applied, by the time the impulse response again had changed. Okay, so that is the in general condition. And in our case, we are talking about the linear time invariant system. That means for each impulse, irrespective of its time instant, the impulse responses are same. So that is the important property of time invariant systems. Okay, so the system is time invariant. So h tau t equal to h naught of t minus tau. So it is basically, what it means is, at t equal to 0, at this point of time, if my impulse response is like this, then at t equal to, let us say t1, after some time, the impulse response will be like this. That means both are same. Only thing is, because the impulse is applied with a delay of t1, the impulse response is also delayed by same instant. So that is what is the time invariant system. So that is what is shown here, because this h naught here, so this is, in this expression we are calling this as h naught t, and here it is h naught t minus t1. Basically this is t minus t1 in the figure, and in the equation I have used that as the minus tau. So minus tau means, so t1 equal to minus tau, so h equal to t minus tau. So this is what we have. Okay, so this is what we have, time invariant system. Now the total output will be y of t equal to integration minus infinite to plus infinite scaled impulse at that time and impulse response at that time, which is not varying with time, then d tau. So this is called famously as convolution integral or superposition integral. Why it is called superposition integral? Superposition integral means because you are superimposing so many impulse responses. Okay, so that's why it's called superposition integral also, because this total operation is superposition of so many impulse responses to get the output basically. So I have explained in my previous lecture about the how a convolution operation takes place by taking discrete values, and you can refer that one. So here this integral equation, convolution integral, can be shortly denoted as y of t equal to x of t convolved with h of t. So the operation, convolution operation, is indicated by an asterisk. So here I am showing two signals. Let us take the blue signal as x of t, then green signal, that is f2. Here it is f2. I call this as h of t. Now what I have to do in convolution? So this is x of t, this is h of t. So what I have to do, this is with respect to tau. So what I have to do, I have to take the second one and lateral invert this one by using minus sign here, then shift it by t. Okay, so here you should not be confused with the t, small t. Small t is not the variable we are considering. Tau is the variable which we are considering. So here minus tau is there. That means lateral inversion, and the plus t, that means shift is t here. So this is what you have. Let us see. This is what is here. You have inverted, time inverted mirror image of the second signal. This is the first signal as it is. You have kept this one on the left hand side, and it moves slowly towards this, and you are multiplying both signals. So it is moving like this, and so you are multiplying these two. There is no overlap, so it is 0 here, and now the signal overlaps first time. So there is area, red area here. This is the area which you are which is equivalent to the height of this red dot here. Okay, so here area is more, so here the maximum area is there. So this is the value of the area, and again this area is coming down, so the area is shown here in the second plot like this. Okay, still it is coming down, still it is coming down. The signal is going out, second signal is going out of the first signal, so it will stop here. Now after that what will happen? Almost the value will become 0. So this operation is called the convolution operation here. Okay, and here shift is given 1.75 like that. And with that you can see it is this is the source of this illustration. You can go to this link and you can see some more examples, interesting examples there. And so this is how the convolution. Then let us take one example. So I have here a given signal e to the power of minus at. This is exponentially decaying signal. So it is nothing but this signal, second signal here, x of t. A is a real constant which is greater than 0, means positive real constant, and h of t, impulse response of the system is, what is the impulse response of the system? Impulse response of the system is the step function here. So we have to convolve these two. If I want to get the output of this system, I have to convolve the input signal with the impulse response of the system. Now, so what is the inversion here? This impulse response is laterally inverted like this, and it is moved like this. As I have shown in the animation, it moves like this until it reaches this 0. Until this reaches 0, there is no output here. Okay, this is moving like this until it reaches 0. There is no output here because this waveform multiplied by this waveform is 0 here. So after some time slowly it moves and it enters the positive axis. At this point of time, let us consider at some t, what is happening here. At some t we have let me change the color of this. So at this point of time, what is the overlap here? So here this is the area of the signal, input signal, and this is the area of the impulse response. These two are overlapping. This is the overlapping region, and you have to multiply this and this both. You multiply this both and find the area under the product. So if I do that, so this is the multiplication part as individual term for a given t. For a given t, so this is between 0 to t, correct? So this is between 0 to up to t only we are taking. This is 0 up to t. So that is why the range is 0 to t. And what is the shape of this one? It is a decaying exponential. So this is the shape of this one. And what about this? This is unit, because unit step function 1. So that's why 1 multiplied by e to the power of minus at. Okay. Otherwise it is 0. At other places it is 0 when there is no overlap. Now, so this is what we have, and this is what unity, and this is the impulse response. So this is impulse response is, sorry, so I have a correction here. So input signal, this is the input signal, this is the input signal, and this impulse response is 1 here, this is 1 here. So when I integrate this between 0 to t and substitute after integration, I am going to get 1 by a multiplied by 1 minus e to the power of minus at. So this is exponentially decaying function. 1 minus e to the power of minus at is a exponentially increasing function which is starting from 0. So the maximum value it takes is 1 by a. Okay, that is at t equal to minus infinity. At t equal to minus infinity, that is minus a into infinity to the power of minus infinite. So 1 by e to the power of, so this is nothing but 1 by e to the power of minus infinite. Sorry, e to the power of plus infinite here. So 1 by infinite is 0 basically. 1 by infinite is 0. So the maximum value will be at t equal to infinite. At t equal to infinite, as t tends to infinite, for example, this integral will become 1 by a 1 minus 0. Okay, so that is nothing but 1 by a. So this is the steady state response. Basically, when this is reaches the constant value at infinite, then this is nothing but your steady state response. So it is slowly reaching the steady state value, that is 1 by a, and this is nothing but this is exponentially charging curve of a capacitor. Basically, in physical circuit analysis, you can call this as a charging capacitor. It is the charging voltage of a charging capacitor, and this is charging, or the curve is starting at t equal to 0, means, so it is, you can multiply this given signal with unit step function, means its range is between 0 to infinite. Okay, so its range is between 0 to infinite. This is for t greater than or equal to 0, you will have the output. For t less than or equal to, you do not have any output. So okay, so that is the meaning of this. Now let us consider some properties of this. Commutative property. Convolution is commutative operation. X of t convolved with h of t equal to h of t convolved with x of t. The order of the signals, order of the functions doesn't matter. Any order you do the integration, sorry, if you do the convolution operation, it gives the same result. So let us take the LHS part and take the definition of the convolution integral, then substitute gamma equal to t minus tau. So this is t minus tau is gamma here, and tau equal to t minus gamma, and d tau equal to d gamma. Actually minus, it will be minus d gamma, and so here you have minus d gamma, and because it's minus d gamma, we have this minus will become minus limit will become plus limit, and plus limit will become minus limit, and again after incorporating this minus 1, and you have minus infinity plus infinity again. This is what you have, and this is the convolution operation commutative, because here in this case x means first x is coming, in this case h is coming. Okay, here you can observe one important thing. So here this is what you have after changing the order. So after substitution of this, so the order of x and h has changed. The first h has come, and afterwards x has come. So by compactly writing this, I have to first write h of t convolved with x of t. So LHS equal to RHS. So it is a simple commutative operation. And let us take about distributive operation. So distributive operation means here you have two impulse responses or two functions h1 plus h2, and they are added and afterwards convolved with another function, third function x of t. In such case, what happens is the convolution distributes over addition. So over addition it distributes. That means the convolution operation I can take individually with h1 and h2, and afterwards I can add. So this is called distribution property, as in any linear algebraic problem. And what it means here is, let us take x convolved with h1, I will get y1 here. Similarly, x convolved with h2, I will get y2. So diagrammatically, this is y1, this is y2. When I add these two, I am getting the actual output. So what is this one? This is nothing but your RHS. So the total output is nothing but, this is what RHS. And what we are doing, these RHS, let us start with these RHS and apply the commutative property. Here x of t h1, they interchange their position. Similarly, this will interchange the position here. So after commutative property, what you have, h1 is coming first, x is coming next. So here what is the in the diagram, what it means is this h1 has come out, is applying as input, and this input is becoming the impulse response. They have interchanged this. Okay, so h1, now h1 is considered as the input and x is considered as the impulse response, but still the output is y1, here the output is y2. Same thing is applicable for h2 also. So h2 here becomes the input to the second block, x becomes the uh, impulse response of that one. Okay, so now what happens, so here we have h1 and h2. I can add now because h was common, so I am taking the h of x common. So h1 and h2 first add, afterwards you convolve. Again I will get the same output. So mathematically I'm taking h1 plus h2, then you are convolving with this one. Okay, that is so from this block diagram. Now, so these two parallel inputs means h1 plus h2, correct? So this is nothing but at this point, if I take, this is h1 plus h2, h1 plus h2. Now again use commutative property. Take this h1 and h2 input into the box, that is as impulse response. Take this x as the input here. So that is what is done here. X of s is moved to left and h1 plus h2 is moved to right. So this is what happened. Now by moving this one, I got the LHS basically. So I started with RHS and this is RHS basically. Yeah, sorry, this is LHS and I started with RHS and I got the LHS. So the property is proved. So this is nothing but distributive property. This is proved. Let us consider the associative property. Now associative property, here you are associating, initially you are associating h1 and h2, keeping them in the brackets as a single identity. Then this identity is convolved with the third function. So this is equal to, you can take the first two as set and afterwards you can convolve, both are same. So you are associating the pairs in a different way. That is what is the meaning of this one. Now let us come to the proof. So the proof goes like this. X of t convolved with h1 of t convolved with h2 of t in the brackets. So x of t as it is I am taking, and h1 h2 are in the convolution integral like this. Okay, now what I have to do, so now what we do is, and this outer convolution we have to implement now, and this is x of t. So this is the integral, outer integral, and this is the signal, and the dummy variable here is x of psi. Earlier it was tau, in the previously case it was tau, now it is psi. And what about this total integral, and where is the t term is coming, t minus, so delay, already t minus tau was there already, so in addition to that you have minus psi also, that is the delay. So that minus tau minus psi delay you have to apply for this term which has a t variable. For this only you are applying the delay. Now you have the variable of integration as psi, and you have a variable integration here, sorry, So this is the psi is there. Okay. Now this is what you have substituted for the, this is the inner integral and this is the outer integral. Now this one, this you can take, interchange the integrals. So this tau integral becomes, the inside integral comes out. Now because tau h2 comes out, because this integral, inner integral, this is nothing but inner integral, it is coming from here to here. So this outer integral is coming here. So this outer integral is coming here. So along with that one, x term is also coming here. So this integral is coming here, x is coming inside, h2 is going outside, then this remains as it is. Okay, just a rearrangement of these terms, and this is external one, because this external one is going inside. So this d psi goes inside, d tau goes to outside, it goes outside. Okay, so now consider this inner integral for which the variable of integration is psi. So this equation can be replaced. This is nothing but convolution of x and h1, but considering t minus tau, correct? So this is the t variable now, and psi is the delay variable. So this is so t minus tau. This is the t minus tau is carried here. Then this is convolution of x and h1. Now leftover part is the outer integral. So if I consider this outer integral, and this is what is inner integral, and this is outer integral in the compact form. This integral can be compactly represented with a convolution operation like this operator. Okay, so this is what you have, and I mean, if you expand this in terms of independent variable, you have this. So we have started with left hand side here, and where h1 h2 are together, then we have reached the right hand side where x and h1 is together and h2 is outside. Okay, so hence this. Now let us consider the memory property. A system is memoryless if its output at any time depends only on the input at the same time. That means it is not dependent on the previous inputs. The output only depends on the present input but not on the previous inputs. So to make it happen, in the convolution integral, the impulse response of the system must not contain any time shifted inputs. So this can be true only if impulse response equal to a delta function. There is a delta function which is occurring at t equal to 0. At other places all are zeros. So if the impulse response of a system is a delta function or a scaled delta function, k can be some value, any value other than the infinite, some finite value, and it can be minus also, it can be plus also, but it is a constant value, a scalar value, and this is this acts as the amplitude of the unit impulse. If I don't take k, it is unit impulse. If I multiply the delta function with k, it is a scaled impulse basically. So the impulse response must be a scaled impulse. In that case, the system becomes totally memoryless. If it is not true, then the system has a memory. That means the output depends on the present input and or previous inputs also. So thank you for your attention, and first 4 properties I have discussed now. In my next lecture I am going to discuss the next properties, that is 5th property onwards I will be discussing in my next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.